We have graphed linear equations. We have graphed systems of linear equations. We've graphed linear inequalities. And now lastly, our last video on graphing for a real long time is how to graph systems of linear inequalities. Is it hard? Well, that depends. If you can graph a linear inequality and shade appropriately with the solid line or the dashed line appropriately and get it right every time, then no, this piece of cake. Because what is a system really? A system is really just two things put together for us. Well, with linear equations, we knew how to graph lines. Then we just put two of them together and found out where they cross. Here, this is even easier. We know how to graph linear inequalities, and we know how to shade. So can we graph two linear inequalities and find out where their shadings cross? Think about the comparison here. What we just did, what I just said. We graphed lines, then we graphed systems and found out where they cross. Where they cross, that intersection, where the two lines met at one point. That one point was the solution to the system. Now, with linear inequalities, we have more than just one point. We have graph a linear inequality, shade the appropriate side. Graph another linear inequality, shade the appropriate side. Their shadings are going to cross either here or down there or there. That's hard to do. I don't have a third hand. Thankfully, it look really weird. But where their shadings intersect, that is your solution set. So when we did this with get the analogy here, with linear equations, we found their crossing. It was one point. You were able to write the solution as just an ordered pair because there was just one of them. There's only one point where two lines cross. That's it. But now with linear inequalities, we have a half plane and we have a half plane. Where those half planes intersect, think of it like a quarter plane if you want. That's going to be your solution set. So we're not going to be able to write out single point anymore. We're going to have to graph it. And we have to graph it because there's a whole lot more than one point. There's an infinite, like quarter plane, if you will, of solutions here, a whole solution set. So we're going to, basically what this all boils down to is, man, graph one of them, shade it. Graph the other one, shade it. Where they intersect, that is your solution set for a system of linear inequalities. So is it hard? Not really. You're just doing two of them at once. That's basically it. I referenced it in the last bit of the last video, but now we'll try it. Also, if you're having if you don't know what these things mean, that little kind of curly bracket, that means it goes together. That means it's a system. So this is supposed to be graphed on one set of axes, other set of axes. This one is as well. If you're having a hard time, I'm going to show you how to draw it. A lot of times when I start out, it would look like this. You go, man, it looks awful. How do they do that so nicely? Well, just graph or draw an elongated S and a reverse elongated S. If you just think about that when you're drawing it, it goes a lot better. It makes a lot nicer looking bracket. So S and reverse S. Anyhow, let's go ahead and do this. So what I don't want you to do is try to graph both lines and then try to figure out on your own where the mutual shading would be. You can. That's one way to do it. Some people do it that way. It's okay, I suppose. I don't like that way because I get lost. So what I want to do is I want to ignore this one. I want to graph this completely along with its shading, and then I want to do the other one. So that's one method on how to do this. So I'm going to completely ignore this. I'm going to pretend that this one is a line. I'm going to use my intercept method because I have variables on one side, non-zero constant on the other. So I'm going to let y equals 0. You know what I'm going to do down here is going to get too scrunchy up there. I'm going to let y equals 0, and that gives us negative x equals 4, or x equals negative 4. Hey, that's an x-intercept. Negative 4 is 0. If I let x equals 0, that's y equals 4. That's a y-intercept, 0, 4. So right now I know that I have negative 4, 0, and 0, 4. And I'm going to graph that. So I'm not even worried about the system right now. I'm just doing one linear inequality at a time. Much like graphing systems of equations. You really didn't worry about the intersection if you were graphing them until after you graphed them. Same thing here. We're not worried about the intersection of the shade until after we've graphed and shaded each one. Also, I graphed a solid line because I had the equals. You remember that from last video, hopefully. Now, we're not done. That would be an equation. Now, I just pretended that that's a line so I can get the separator of my half plane for that particular linear inequality. Now we have to determine what half plane is actually a solution. We do that by testing one point, checking one point in the original inequality. I'm going to check 0, 0 whenever possible. So I'm going to check 0, 0. I'm doing it in my original inequality. Hey, that's 0 minus 0 is more than 4. Yeah, that's false. That's for sure false. 0 is not more than 4. That said that this is false. That says this whole half plane is not true for that inequality, for this situation. So if this is all false, this is all true. You're going to notice something else. I'm drawing pretty long lines and a lot of shading because what we're looking for is where the shading intersects. Just like with systems of equations, we looked at where the lines intersected. That was our solution. Well, now that our solution is shading, we're looking for where the shading intersects. So that's that's half of it. Now we're going to do the other half. We'll do the x plus 3y is less than negative 2. I like to use two colors here. I know I'm using purple and black, and it doesn't have a whole lot of contrast, so you might have a hard time seeing it, but other colors don't show up very well on video for me. So I'm going to use purple to do this linear inequality. So I'm going to pretend it's a line. I'm going to use my intercept method. So I'm going to let y equals 0. I'm going to get x equals negative 2. That's our x-intercept. I'm going to let x equal 0. I'm going to get a y-intercept of 0, negative 2/3. That's right about here. 0, negative 2/3. I also have negative 2 for my x-intercept, negative 2, 0. So I'm going to graph that. Now, what line should I use here? Should I use a dotted, or I'm sorry, a dashed or a solid? Well, one of them if I keep my line straight. Because I have that strict inequality, it says you're strictly less than, not equal to. You can't be on the line here. I'm going to use that dashed line to represent that. Now, can I still check 0, 0? Well, of course I can. That's why I use a different color pen, so that I don't get confused with my false being false for this one as well. So I'm going to check 0, 0 again. This time I'm checking it in purple. I'm going to check 0, 0 in my original inequality. Zero's less than negative 2. Oh, no, it's not. I know negatives are less than 0, so this is not true. It's also false. So I happen to get two falses. False for the first inequality, false for the second inequality. Now notice, I haven't even looked at the black inequality right now. I don't even care about that one right now. I'm focused on the purple inequality. So I tested this point again. It was also false, representing that, ignore this, all the black line and shading. I'm looking at the purple only. According to this line, this half plane, this would be the false half plane. This would be the true half plane. So all this stuff over here would be true. This is false, this is true. Here's the idea, one last time. Where equations intersected was a solution to the system of equations. Where shading intersects is where we have the solution set for a system of linear inequalities. So we don't just have one answer. We have a whole bunch of points. It's all right. Well, let's look. Here's one half, here's the other half. Not here. All these points, these ones, these work in the first inequality only. All these points here work in the second inequality only. All these points work in none of the inequalities. These points right here, where we have both purple and black shading, that is what we're looking for. That's the solution set. Right there. Those points work in both, and we can prove it. Try a point over here. How about like a negative 5, 0? Should be a point in there. Negative 5, 0, that's negative 5 for x and 0 for y. 0 minus negative 5 is 5. 5 is more than 4. Yeah, it works. But also, negative 5 for x plus 0. Negative 5 is less than negative 2. That also works. That's what we're talking about. All these points in that little, looks like a triangle almost, going like this forever. Those are all the solutions. Those are all the points that are solutions, hence our solution set, and that's the overlap of the shading. That's what we're doing. We're graphing one like normal, graphing the other like normal, and just looking for the intersection of the shading. Let's try that a couple more times. So we have another one. Now, we're going to start getting to some I want to give you weirder graphing where you can't necessarily use intercept method. This one looks pretty good for intercept method. This has variables on one side and non-zero constant on the other. I'll pretend it's a line. It's not going to be that bad. This one doesn't have that. This has, oh man, what would you do there? Well, even if I subtracted y from both sides, which I get a lot of students saying, let's subtract y. If you do, can you use the intercept method? 0, 0, that's a problem. Because you'd have 0, 0 twice. That would tell you you're going through the origin. Yes. Because you don't have a constant. Yes. You don't have a constant here. Nope. That means that you're going through the origin. Intercept method does not work if you're going through the origin because you're using the intercept at the same point. That's a problem. So instead of that, excuse me. Did you just say bless you? You better have. Man, I deserve your blood. I deserve that. Bless me. Anyway, that was weird. Sorry about that, guys. You'd reverse this. So get your y on the left-hand side. Sure. That means that we'll have take the whole thing off, reverse it, put it back. Y is on the left, 4x is on the right. And because we're reversing the entire inequality, the inequality has to reverse. Now, if we pretend that that's a line, just pretend. We have a slope. Sure, what's your slope? What's your y-intercept? Well, we already determined the y-intercept is 0, but it's really clear here. We don't even have a constant. It's a 0 constant. 0. We from there would go, I hope you remember it. I hope you remember slope. From the point, from our intercept, we'd go up 4 and right 1. Now, would you graph it solid or dashed? What would you graph it with? Well, let me look back at there. That's got to be solid. It's still going to be solid. You just reverse the whole thing so we get a better picture of the slope-intercept working for us. And then we're done. Oh, no, not even close, really. We still, firstly, with this inequality, have to determine the half-plane. Will 0, 0 work as our checkpoint for this particular inequality? No. No. Not if you used something that, well, not if you use 0, 0 as an intercept. You can't also use that as a checkpoint because it won't tell you an appropriate half-plane. Use something like 0, 1. That's what I use. 0 for x, 1 for y. In the original inequality, 0 for x and 1 for y. So I'm going to check that. Zero for x, 1 for y, which is true. That says that point, that's true. That says, hey, that point right there, that is in the correct solution set. So it says all these points over here, if that point's true, it's saying this is the working solution set. 0 is less than 1. Yes. Get so used to false ones, sometimes you want to mark them all false. But 0 is less than 1. That's a true statement. That point is true. This half plane is true. All this stuff over here is true. Maybe double check. Sometimes you can catch a lot of mistakes that way by double checking. Check a point over here and make sure that these points are false. So check a point like 5, 0. It's easy to make mistakes on this. Trust me. I make them often sometimes if I'm not really focused on it. So try 5, 0. 5 for x, 0 for y. It should be false. 20 is less than 0. That's false. Good, okay, so all these are false points as well. Now, we've done half of our inequality. Let's do the other half of our system. Let's do the other half. So I'm going to change colors here. So now I want to pretend that this is a line. I'm going to use intercept method because I have variables on one side, non-zero constant on the other. Looks pretty good. X-intercept of 9, 0. All right. And now we plug in x equals 0. Y-intercept of 0, 3. 1, 2, 3. Now I'm pretending that the black line, black shading is not even there. I'm going to do the purple right now. That goes through 9, 0 and 0, 3. That's the line that this inequality is based on. However, the line itself, man, it's not even included. That's got to be a dashed line. You know what's interesting as we're doing this? I suppose that we sort of care where these lines intersect. But that point where they intersect, that's not even a solution to this system, because it'd be a solution for the line that's solid, but not the line that's dashed. So we're really not worried so much about the intersection point itself. We're worried more about where the shading intersects, where the half planes intersect, and we're about to find where that's at. So we have to test one more point. Now notice, I don't even care that 0, 0 didn't work in the first inequality because it does work here. I don't care that it doesn't work in one if I'm focused on another one right now. So I can still check 0, 0. I'm really viewing this as two different inequalities graphed on the same graph. So if I can't use 0, 0 for one inequality, it doesn't mean that I can't use it for the other. You very well could, as long as that line doesn't also go through the origin. So I'm going to check 0, 0. If I do, I'm checking 0, 0 in the original inequality. Always goes back to the original. So 0 is more than 9. 0 is less than 1. That's a true statement. 0 is less than 1. 0 is more than 9. That's a false statement. 0 is not more than 9. So that says that this point is false. That says that according to the purple dashed line, all the points over here on this particular half plane, the line separates your plane into two half planes. This one is the false one. This one is the true one. Maybe double check that. Check a point over here to make sure that you correctly shaded the appropriate half plane. Check something like, let's see, 5, 5. You do 5, 5, that's over here somewhere. So if we check 5, 5, 5 plus 15, that's 20, that's more than 9, that's okay, that's true. So I know that this is the true half plane as far as our purple line is considered. Now, do you see the intersection? Because as far as systems are concerned, it's all about the intersection. We had that with equations. We also have it with shading here in inequalities. This would just be the points that worked in this and not the other. This would just be the points that worked in this and not the other. This would be points that work in neither. The overlap is points that work in both. That's our solution set. If you're asking, well, don't we have a more concise way to represent the solution set than graphing it? Not really. How else would you list out all those points that work in both inequalities? Because that's what we're looking at. And those points do work in both inequalities. So let's look at the next one. Try this if you want to. See if we had this in the last video, something very similar to this. See if you can do it. See if you can graph that inequality. Shade the appropriate side. See if you can graph that inequality. You can't use intercept method. Notice that. You can't use intercept method. See if you can solve that for y and graph that inequality. See where the shading overlaps. All right, so if we're going to start this off, it doesn't really matter which inequality you start with. I'll start with the top one. So I'm going to pretend that this is a line. I really don't want you just saying, well, replace it with equals, because I don't really want you replacing anything. I don't want you even considering that this is this. I just want you considering that this line is the boundary of the working half plane, of this, the half plane is the solution set. We have to graph the line to separate this plane into a half plane. So we're pretending this is a line just to find that boundary, so to find our boundary line. In this case, oh man, I'd love to use the intercept method. It's my favorite method, if you haven't noticed. I try to do everything with the intercept method. It's really quick, but if I need the slope, it's a drawback, and if I have a zero, you can't do it. So I'm going to have to solve this for y. If we do solve this for y, we get something that's very graphable. Now, one last thing. If you were going to use that one technique where you look at the inequality in order to graph the side, so I referenced that in a couple videos. If you're going to do that, then you have to keep this inequality with it, because if you were to divide by a negative, that inequality would flip. It would reverse itself. So it's a big deal. If you're going to use that technique, like, oh, it's down or above, you can do that as long as you solve the inequality with the actual inequality in there. So as long as you solve for y with the inequality there. Because if you were to divide by -5, your inequality would reverse. That would be a problem. So if you're going to do that, solve it with the inequality. And then at this point, be like, okay, well, now I'll pretend it's a line. So now I'll pretend it's a line. Now that's something I can graph. Same result as far as your equation goes, but different result as far as interpreting the half plane. So from here, I know that my intercept is 0, 0. That's why we couldn't use intercept method in the first place. So we have a 0, 0. And then from there, our slope tells us we're going to climb 2. We're going to go to the right 5. Now, I'll graph this with a dashed line, and you should know why. I'll also shade this. So this is what I was just talking about. If you like the idea of my variable's on the left-hand side, it should tell me whether to shade above or below. It does. If your variable y is on the left-hand side and you have that arrow pointing left, that translates to down for the y number line. So I'm guaranteed I'm going to be shading this lower half plane. You can do that as long as you solved for y while including your inequality. If you haven't, then you don't get to do this. So I know I'm going to shade down here. Now I can also test a point, but it's not 0, 0 because I'm going through the origin. If I test a point like 0, 1, so check 0, 1. So if I check 0, 1, that's 0 for x. Plus 1 for y, that gives me 5 less than 0. 5 is not less than 0. That's a false statement. So again, I get the result that this half plane is not the true solution set half plane. This half plane is. We do the exact same thing for this. Oh man, bummer. You know what, I'm going to change this. I'm sorry. If you did it on your own, you probably found out the hard way, but our solution set wouldn't be till way over here, and that's off your, it's off your camera. So I'm going to change this to 1. But I'm the teacher, I get to do stuff like that, so sorry, sue me. If I change that to 1, you're watching videos for free anyway, you know? It's kind of cool. So if I change that to 1, let's pretend that's a line. Y equals 1, y equals 1 is a line. It's a horizontal line. It goes right through here. And then we drew it solid because we have the equals. It says the line's part of my solution set. Now, Where do I shade? This is set up properly for this interpretation. Y is on the left-hand side. It says shade below, shade down. So less than points down on the Y number line. If you wanted to test a point, you test a point like 0, 0. You can still check that for this inequality. Notice, this doesn't go through the origin, so you could check the origin. 0 for x, can't plug in the x, who cares? 0 for y. 0 is less than 1, true. It says that this is on the proper solution set side. So in either way, you get the appropriate shading. Sorry about the change there, guys. I really am. I feel bad about doing that, but I think I wrote it down wrong to begin with. So when I saw the 3, go, oh, that's a problem, because this would intersect till way over here, and we're finding where our shading intersects. And so to show that, we would get not this little area, but all of these points that's double shaded. So the overlapping of this half plane and this half plane, that's our solution set. Looks like a large one. They're all an infinite number of points. Some just look larger than others. Anyhow, we've got one more. This one actually kind of an easy one. I just want you to not forget slope-intercept form. If you're given something like this, you do have an option. If you're going to graph this, cool. You may as well try it right now if you want to. I won't change it, I promise, this time. You could add x, and you could do intercept method. That's fine. You could subtract 2x, and you could do intercept method. However, because we have this other technique that's if you solve for y already, you can use slope-intercept method. This is set up perfect for slope-intercept. So let's go ahead and do this. It's going to be kind of a quick one for us. It's just to get you to remember that you can use slope-intercept here as well. So let's do the first one. I'm going to pretend it's a line. In fact, I kind of think these are easier because you don't have to solve for anything. I mean, there's no intercept that you need to solve for. You have no work really to do. So if you pretend that's a line, your y-intercept is 2, 0, 2. Our slope is -1, going down 1 and right 1. Remember that we can always write this as a fraction. So plug in 0 for x, you get 0, 2. That's where we're getting our y-intercept from. The slope-intercept form works that way. From that point, down 1, right 1. We draw our line with a, well, what do you think? What's our line, solid or dashed? Because we have that inequality without the equals, it's saying the line is not part of our solution set. None of those points are going to work. None of them. Even in the system, because the system involves including the points that work in both. So if the points don't work for this line, they're not going to be part of our solution set. How we check? We can still check with 0, 0, or you can use the technique I just showed you. If y is on the left-hand side, you're going to be shading the positive, the up side of that number line. I'll be shading up here. If that doesn't make sense to you, then don't worry about it. You can still test a point. Check 0, 0. So if we check 0, 0 in our original inequality, it says 0 is more than 2. That's false. That says that this half plane is a no-no. That says that this half plane is the true solution set for that inequality. You get the same result either way. It's kind of nice. Now, the last one. If we graph this, I'm going to switch colors. So if we graph this, I'm going to pretend this is a line. Of course, the line is the boundary. The line's the boundary of the working half plane and the non-working half plane, the solution set and the non-solution set. If we graph this, our y-intercept is 5. From that point, our slope is, well, it's 2 over 1. So from that point, we go up 2. 1, 2, 3. Okay, get it right, Leonard. 1, 2, 3, 4, 5. So y-intercept of 0, 5. From that point, we go up 2 over 1. If we do that, we'll graph this with a solid line because it says the line's part of the solution set given to us by that equals. Now, we can still check 0, 0, or we can look at this and say, if this is a number line, and y is the axis we're looking at here, y is on the left-hand side, it says if I looked this way, I'd be going below whatever I'm graphing. That's going to shade this side of the half plane. You can check 0, 0 as well. If we do, this says 0 is less than 5. That's true. Yeah, 0 is less than 5. That's a true statement. That says, according to our check, we got true for our purple line. That says that point is on the solution side of our half plane. That's the working half plane over here. And we can clearly see in this example where our overlapping solution sets are. So these points must work in both of our inequalities. And you can check one if you want. Check a point like 2, 2. It's got to work in both. Plug in 2 here, that would be, well, if I do 2 and 2, 2 for x and 2 for y, that's a point somewhere in here. Then we would get 2 is greater than 0, true statement. Or here, 2 is less than 9, also true statement. I know that a point over here works in both both inequalities, giving us a pretty good indication that we have the correct solution set for this system. That's it. So analogous to graphing a system of linear equations where we get an intersection and that's a point. Now we get an intersection of half planes and that's a whole solution set of points. I really need you to get that idea that we're really graphing in order to represent the solution set. We're not graphing for funsies. There's not another way for us to really write out the solution set awesomely, unless you want to write out every little point, but there's an infinite number of them, so that'd take you forever. So graphing is the way that we show solutions. Graphing was the way we showed solutions for lines, for linear equations. That was the solution. And now the same thing happens for linear inequalities. We're showing a solution to both of these inequalities. It just happens to be where the half planes overlap. I hope you get it. I hope it makes sense. I hope you're feeling very confident in this. And I'm hoping you're seeing the value in your graphing that you learned, so you worked so hard on, because now it makes this stuff a lot easier. If you can graph accurately and test one point, it just shows you. It shows you whether one side of the graph is true or false, whether one side of the graph is a solution or not. If we get true for that test point, it's that side. If we get false for the test point, it's the opposite side. Now we're putting them together for systems of linear inequalities. Do the same thing twice. I'll see you in a little while. We're going to do another video. We're going to talk about exponents. So we're done graphing for a while. We're going to get really good at exponents so that when we get to factoring, we know what to do. So I will see you around for the next video in just a little while.